Alright, so you're going to have lenses. Alright, and so a couple things you need to know. I can email these notes to you if you want. Alright, so have lens, or you can take notes whenever you want. So have the lens equation, 1 over f is 1 over q plus 1 over p. Our magnification is negative q over p. And it'll help you. You're not going to have any ray diagrams except for the convex lens when it's outside the focal point. So remember, with the convex lens, we had 3 scenarios like this. I can have an object outside the focal point, an object at the focal point, or an object inside the focal point. And in each of those cases, well, first, you'll need to know how to draw the rays for this case. So if I have rays parallel to the axis through the focal point, parallel to the axis, and then I can also have a ray that goes straight through the center of the lens, like that, unrefracted. Those are the 3 rays. It'll be one of those where I give you 3 rays and 3 or 4 rays, and you tell me which one is incorrect. So the image here is over here. So in this case, I have an inverted real image. You'll also have some questions about just what type of image does this lens form in this scenario. So in these other cases, I get no image here. That is that q is equal to infinity. It works out that if f is equal to p, that q is equal to infinity. And then over here, this is my object. My image is right here. So here I get a upright. All upright images are virtual, because in order to be upright, this has to be positive. In order for this has to be positive, this has to be negative. So all upright images are virtual, and then it's also going to be bigger. This is a magnifying glass, okay? So you need to know those 3 scenarios, and then also with the concave lens, if the object is anywhere, I'm going to get an image that is upright and virtual. Be bigger. No, actually no, it's always smaller. I'm sorry. So my image is actually smaller. Okay? You following? All right, so also remember that for these, I have a positive focal point for convex, a negative focal point for concave, and then also the focal length is equal to the center of curvature divided by 2. So I'll never tell you the sign of the focal length. In fact, I might just give you the center of curvature, and you just need to know for a concave lens it's going to be negative, for a convex lens it'll be positive. Also in this chapter, you need to know about our aberrations. We had 2 aberrations. We had chromatic, and we had spherical. You need to know what causes them, how to fix them, and when they take place. Chromatic occurs only in lenses. It's due to the wavelength dependence on the index of refraction. So red light, for example, will bend less, or will bend differently than blue light. Spherical lenses, or spherical aberrations, occur in lenses and mirrors. It's due to the spherical geometry. And it occurs because light rays focus at different points, causing a fuzzy image. So just note, you'll have 1 or 2 questions about that, just asking about what causes this, where does it take place, that kind of business. See, I think that was it for chapter 7. You're going to have a couple of questions that'll have, I give you a lens, I ask you for the magnification or the image distance. Oh, you will have a 2-lens problem where you have 2 lenses. We worked like these in class. It will not be like the one that you had in lab where you had a virtual object. So it'll be, I have an object here, it creates an image there, I have another image here, that sort of thing. We did a couple of those in class, and there's one in the homework, but not one where P is negative. So you will not have one where you have to have a negative P. You worked through one of those? Yeah. Yeah, I think it happened in lab, but it...
I think this one's a simpler.
This one's a simpler way, yeah. You just treat it as 2 separate problems. Just when you calculate, when you find Q1, then this is going to be P2. So I'll give you this distance, say L, so P2 is equal to L minus Q1. And then you just work it just like you did before.
I think for phenomenal studies, I always have trouble wondering why I have to use this one or why I have to use that.
Yeah.
Like, I'm not really sure. Still.
Okay, we can take a look at some problems. Let me just sort of finish. We'll go through these other chapters. We'll go back and look at problems. Okay, that's it for that. For chapter 8, you have interference, so you need to know out of phase, in phase. Out of phase, you need to know 0, 90, 180, and 360. How to identify each of these. So 0 and 360 would look like this. This is 0 degrees, 360 degrees. That means they're in phase. And then also their path length difference, I'll call it PD, is equal to 0, 1 wavelength, 2 wavelengths, and on and on. That'll come up actually both with sound and with light. So you'll see a couple of different questions like that. Interference of light. When they're in phase, when they're peaks and peaks, troughs and troughs line up, they have a 0 path length difference, 1 wavelength, 2 wavelengths, and we call that 0 degrees and 360 degrees out of phase. If they're completely out of phase, so that's one scenario. The other scenario is when they're completely out of phase, like that, where their peaks and troughs line up, that's going to be 180 degrees, and that is when they are half a wavelength path length difference. So lambda over 2, 3 lambda over 2, 5 lambda over 2, and on. All right? So I skipped there because 2 lambda over 2 is 1 wavelength. 4 lambda over 2 is 2 wavelengths, and that would be in phase. And then in between is when I have 90 degrees, so that would look like this. I'm offset by a quarter wavelength, so it's gonna, it's a little difficult to draw, but when you have a peak that doesn't line up with a peak, or a trough, or a peak doesn't line up with a trough, if it's somewhere in between. So they're shifted so that they're neither constructive nor destructive, neither total constructive nor total destructive, then that's going to be 90 degrees out of phase. Okay? You follow me on that? So if it's neither constructive nor destructive, that means it's 90 degrees. Okay? All right. So now to identify those, like I said, it comes up with sound too. And then we had double slit, single slit, and diffraction grating, and that was it on this chapter. Double slit. Now, first of all, for all three of those, you to identify, if I show you the pattern, this comes up in some of the old exams. If I give you a pattern and I say, what is the path length difference here for this dark fringe? Then you would say, well, this is 0, this is a half a wavelength, this is 1 wavelength, so this is 1.5 wavelengths, or 3/2 wavelengths. Okay, or if I said, what is the path length difference here for 2 waves that create this interference pattern? You'd say this is 0, this is 1, this is 2 wavelengths. Okay, see some old questions like that on the old test. That's for single slit, double slit, or diffraction grating. For a single slit, you need to be able to know, actually for all three of these, you need to be able to know how to do certain things. You need to know what is the highest order. You need to know how to find the separation between the fringes. Like on the screen, what is the y distance? And then you also need to know, how to find theta, how to find d, how to find lambda. Just solving those equations for, that would be a pretty easy problem, the third one. Just giving you a double slit and asking you, what is theta, what is lambda, what is d, that sort of thing. All right, these first two are a little more difficult, a little more consuming. So let's look at each of those, okay? So for the highest order, looking at the double slit, for the highest order, that is just a special case when theta equals 90 degrees. We worked a problem like that in class. It just means that the light is going way over here, so it's never going to show up on the screen. So you just say, d sine theta equals m lambda, and then you solve for m, d sine of 90 divided by lambda, so m is just d over lambda, and then whatever that is, you just round it down. So if this comes out to be, I don't know, 3.7, then you have 3 orders. Okay? Be careful. So for example, let's say that you found that m was equal to 2.9 or 2.8 or whatever. That would mean that you would have 2 orders on your fringe. And I could ask you 2 things. I could ask you, how many orders are there? And you would say 2. But if I asked you how many bright spots there are, you would say, okay, if you have 2 orders, how many bright spots are there? I have one up here, one right here, one right here, one right here. You have 5. So on these questions, I could ask the orders, in which case the answer would be 2, or I could ask you how many spots there are in the interference pattern, in which case the answer would be 5. Okay? I don't remember. I do ask you this question. I don't remember what I asked. So if I ask the order, are there bright spots? Just read it carefully and make sure that you understand what's going on. Okay? You could have some lower order questions that ask you just what is theta, d, or lambda. I would give you the various quantities and ask you, what is theta? So you solve this for theta. Or what is d? You solve it for d. Or what is m? And you solve it for m. Okay, that's double slit. Single slit is very similar, and you will have a single slit. Oh, I'm sorry, there is another problem. So I could also ask you, either for double, single, or the diffraction pattern, what is the distance between the fringes? And I'm pretty sure I do ask you this. And what that means is, what does this distance say to the first order fringe? What is y equal to? Alright, the first thing that you do is you find theta. So we have our d sine theta equals m lambda. Is this too fast? Is this okay? Okay. So I have d sine theta equals m lambda. I solve for theta, and then I find y. Solve this for theta. We can look at a problem if you want. And then I find y. I have this triangle. It's L on this side, y on this side, theta on this side. I do my tan theta. I say tan theta equals y over L, so y is equal to L tan theta. And then that would be your answer. So that would be a question where I ask, what is the separation between the fringes? Between the first order or the 0th order fringe, and in this case, the first order fringe. Okay? Alright. Single slit. It's very similar. You'll have see similar questions. The only difference is this is A, and then our interference pattern looks a little bit different, but here, whereas before we had d sine theta equals m lambda, now we have a sine theta equals m lambda. A is the width of the slit. M now is going to be 1, 2, 3, and up to the maximum number of orders. Now, with double slit, it started at 0. With single slit, it starts at 1. That's because this is our first order. This is our second order. It counts down the number of dark spots, not bright spots. That's on your equation sheet. Make sure you're clear with what's on the equation sheet. But on the equation sheet, it says theta dark instead of theta bright for the single slit. Okay, so just make sure you're aware of that. Diffraction gratings are very similar. The only difference is that when you see a diffraction grating, I'll tell you the number of lines per millimeter, for example, or number of lines per centimeter. You'll need to convert that into distance. So let's say I have 10,000 lines per millimeter. I'd have to find d, which is going to be the inverse of that, and that's going to be in millimeters. In which case, you'll need to make sure that you convert it into meters. We'll look at some problems like that, but make sure that you do that, that you watch your units. In fact, there's a number of places where you have to convert units, where you have to go from millimeters or micrometers or nanometers into meters. And just be careful, you always convert all those to meters. okay? It comes up probably 4 or 5 times where you have to convert units. So make sure that you're quick with that. All right, and then we're on to sound. Unfortunately, there aren't any practice test questions, but look at the quick test questions in your book. Look at the concept test questions that I sent you, as you can look at the solutions to, and then the homework questions. So I pulled questions from all of those. They aren't exactly the same, but they're very, very similar. Sometimes I might just change the numbers or just change it a little bit, but if you're good on those questions, you should be good for the test. Are you good on those questions? Are you good on those questions? Okay, all right. Well, let me hit the high spots first, and then we'll get down in the weeds. So the hard things that you'll probably see that students have trouble with are the intensity level. Right, this is measuring in decibels. L is equal to 10 log I over I naught, or you could think I1 over I2. Make sure that you can solve this equation for either L or for I, being able to calculate the intensity or the intensity level. So if I'm solving for I, let's just say I want to know what is I. Let's say that L is, 100. What is I? Well, I'd say 10 log of I over I naught. I would divide both sides by 10, so it gets rid of that. So I get 10 log, and then I would raise both sides to the 10th power. Is that right? Did I do that right? Yeah, okay. So this cancels out the log. Just make sure you know how to work with those logarithms. And then I have 10 to the 10th equals I over I naught. I naught is my threshold of hearing. That's 10 to the minus 12. That number is on your equation sheet. You should take a look at the equation sheet. It's updated on the website. Make sure you see what's on there. And then I just do cross multiply, and so I get I then is 10 to the 10th, 10 to the minus 12, so that's 10 to the minus 2 watts per square meter. You have some problems like that where you have to work with that equation, so make sure you can do that. You need to know the different wave properties. We had several like this in the concept test, so working with these equations, V is equal to lambda times frequency, or V is equal to lambda over the period. Working with those to figure out, what is the wavelength, what is the speed, what is the whatever of a wave. And then also we did one similar to this where we have a string. The frequency on a string is 1 over 2L, square root of T over mu. I had a whole series of questions where he asked, what if you change one of these things, like, the mass density, for example. So what if you doubled the mass density? Well, that's going to change the frequency by 1 over root 2. And then what does that do to the speed of the wave? Well, V is equal to lambda times our frequency. If I change my frequency by 1 over root 2, then I'm going to change the speed by 1 over root 2 as well. Okay, that's like those questions we have with a string. If you change the tension, or you change the mass density, or you change the length of the string, what does it do to the velocity? Make sure you look at that. I'm pretty sure there's a question like that on the test. Okay, and harmonics. You need to make sure you know your harmonics for the open-closed tubes, open tubes, and closed tubes. All right, so you need to be able to do two things. You'll need to be able to calculate the frequency for a set of harmonics, and then also be able to identify the harmonics. Let's do the open-closed. Actually, we'll do them in tandem. And then let's do the closed. Don't worry about the open. It's identical to the closed as far as the frequency, okay? But the open-closed and the closed are different. In fact, the closed, we can also think of this as a string. Don't forget you have a node on this end, so it looks like that. Then it reflects back on itself, so it looks like that. Over here I have a node here and a node here. It reflects back because it resonates in the tube. It reflects a standing wave, so it goes back and forth. That's why we draw it this way. One wave goes one direction, another wave goes the other direction. All right, so need to recognize here that within the length of this tube, I have 1/4 wavelength. Within the length of this tube, I have 1/2 wavelength. And if you get that, you should be pretty good. This is my length L, this is my length L. Now, this is the first harmonic. The second harmonic here is going to look like this. Because I'm forced to have a node here and an antinode at the other end, my second harmonic will look like this. So I could give you a picture of these and ask you, what harmonic is this? And the way that you determine the harmonic in this case is you count the number of nodes. All right, so you can say, well, this is one node, this is two nodes, so it is the second harmonic. Or I guess you could count the number of antinodes as well. One antinode, two antinodes, second harmonic. Okay? Notice here, though, that it has 3 1/4 wavelengths. 1 1/4 wavelength, 2 1/4 wavelengths, 3 1/4 wavelengths. If we go on and draw those, we get our frequency, NV over 4L. N is equal to 1, 3, 5, and on and on. Notice these are odd numbers, so be able to calculate for an open-closed tube what is the frequency, or what is the wavelength, because if I wanted to find the wavelength, then I would just say V is equal to F lambda, so it would just be an extra step to find the wavelength. Also be able to identify the resonances. Notice, be careful that my N right here is 1 for the first harmonic, but it's 3 for the second harmonic. N doesn't give you the harmonic, it gives you the number of quarter wavelengths. Because I have 3/4 wavelengths in the second harmonic, that's where this N comes from. It doesn't give the harmonic, the resonant frequency, or the harmonic. Now, on the closed it's a little different. People to identify them, so that's the first, this is the first harmonic. The second harmonic begins at a node and goes through like this. That's the second harmonic. The third harmonic looks like that. Those are a little easier to identify because I got 2 humps, I got 3 humps, I got 1 hump. They're just easier to identify, I think. Okay, but make sure that you can identify these and then also be able to calculate the frequency. This is on your equation sheet, but the frequency is NV over 2L, where N is equal to 1, 2, 3, and on and on. If you want to write the differences here to help you to keep them straight because they're not labeled on the equation sheet, the 4 comes about because I'm looking at quarter wavelengths. The 2 comes about because I have half wavelengths in my tube. Okay, and then I have 1/2 wavelength, 2/2 wavelengths, 3/2 wavelengths, and that's why I go N equal 1, 2, and 3. You will see a couple problems like this on the test for sure, like an identification and calculating the frequency or the wavelength. Okay, we have some other stuff with intensity, speed of sound, Doppler shifting, and stuff like that. Do you have anatomy yet?
No.
Okay, you need to know the basic parts of the ear and the basic parts of human speech. Let me just give you a quick rundown of that. Do you remember it? Okay, well, let me just... Here's a person. Those are your lungs. Diaphragm, right there. You have the trachea, which comes up. Here you have a box called the larynx. Let me just label all this. So lungs, diaphragm, larynx, trachea. Inside the larynx, if I blow this up, it doesn't look like this, it's a different shape, but you know, you get the idea. Inside the larynx, I have the vocal cords. There are 2 muscles that can move, that can tighten or loosen. These are called the vocal cords. They are inside the larynx along with some other things. All right, you need to know those basic parts. Notice that the vocal cords change pitch by changing tension. That's how I modulate the frequency of my voice, right, by changing the tension of my vocal cords. Know that. You also need to know the basic parts of the ear. So my ear, little toy model. Here's a one-eared guy. All right, this is the auricle. All right, this is the ear canal. This is the tympanic membrane, or the eardrum. From there, we get the ossicles. There's something like this. I don't know how to draw them, but these are the little bones inside your ear. The ossicles go into the cochlea. The cochlea is that twisty thing. It's a chamber that's filled with fluid. And the cochlea sends a signal to your brain. That's the auditory nerve. You're going to have a picture of both the speech functions in the body, like how you produce speech, that has all these things: lungs, diaphragm, trachea, and the larynx. You need to be able to identify them, know roughly what they do. The diaphragm forces the air, the lungs contain the air, the trachea is the passage along which the air flows, the larynx protects the vocal cords, and the vocal cords produce the sound. In the ear, gosh, that is a terrible drawing. It sort of made sense when I was drawing it, but the auricle is this part outside your ear. This is the ear canal. It amplifies the sound. The tympanic membrane, or the eardrum, vibrates when the sound wave goes onto it. The ossicles help to amplify that. They're just levers. They're bones that act as levers. They transfer the vibrations to the cochlea. The cochlea converts those vibrations into an electric signal. Okay, this is all should all be in your notes. And then the auditory nerve sends that signal to the brain. There's one other thing. The eustachian tube. The eustachian tube is that tube. It's right behind the eardrum that connects the middle ear to the larynx, or to the trachea. I think it goes to the trachea. But anyway, it's why you get ear infections when that eustachian tube gets clogged up. It's why kids have tubes put in their ears, because their eustachian tubes aren't big enough and they're not oriented properly to drain fluid from your ear. Okay. That's it for the ear. Okay. Doppler Facts. If I have a source of sound, if it's moving towards me, this is the source of the sound. I'm standing over here. This is my observed frequency. So there's a source frequency and there's an observed frequency. In this case, if it's moving towards me, the observed frequency is bigger than the source frequency. It's like a train coming towards you. The frequency gets big, and then as it's moving away from you, it gets small. So we had a couple of equations for that. For when the source is moving, which will usually be the case, the frequency observed is equal to this VW, that's the velocity of the wave, times the velocity of the wave, or divided by plus or minus the velocity of the source. These equations are on your equation sheet. The tricky part of this is have to use the plus or minus, and you just need to ask yourself, is f(oz) bigger or smaller than the frequency of the source? If this is bigger, yeah, if f(oz) is bigger, this has to be minus to make your denominator smaller. There's another equation for when the observer is moving. It's on your equation sheet. You just flip these, okay? So just make sure you know how to use that. There were some homework problems dealing with that. I think that's it. Yes, well, there was the one thing with the intensity of sound. The intensity is power over area. I give you the equation for area. It's 4 pi r squared. Okay, power is in watts. Intensity is in watts per square meter. It's how loud is the sound? How intense is the sound? Okay. We did a couple things, like if I increase this by a factor of 2, that decreases this by a factor of 4, by 1/4, because it's squared. Basic stuff about waves, transverse versus longitudinal waves. They describe what happens to the medium. Transverse waves move the medium up and down. Longitudinal waves move the medium back and forth. Right, what's that? The hugging wave, right? The longitudinal wave is the hugging wave. You move side to side, and sound wave is a longitudinal wave. It's also called a compressional wave or a pressure wave. That's it for... Yeah, I guess, yes. Yeah, I can't think of one right off, but sure. Okay. We'll get some old tests. Okay, we'll just sort of go through them, and if you see anything that stands out to you, let's see. Okay, well, let's say this is a mirror. Yeah, we're not going to do mirrors. Could have to identify a lens. I don't remember actually if you have to identify a lens. There's a... Huh? Yeah, that is. Let's do a different one though, because that one... Let's try this one, okay? Because that one is one that has a virtual object, and you won't encounter that. Okay, so in general for your lens equations, you will have a convex lens for a 2-lens system, but I start with this. This is my P1. This is my F1. So I first solve for Q1. It's going to be 1 over F1 minus 1 over P1, the inverse of that. Okay, I just solved the lens equation. That's 1 over 10 minus 1 over 20. That's 2 over 20 minus 1 over 20. So Q1 is equal to 20 centimeters. All right, and then you need to find M1 now, negative Q over P. Negative 20 divided by P, which was 20, that's equal to negative 1. And then that tells you that my image is right here. It's 20 centimeters. It's inverted because this is negative, and it's the same size as the object. Now, I consider this. What's that? Right, 30 centimeters. So I do it all over again. Q2 is 1 over F2, that was 15, minus 1 over 30. It's 2 over 30 minus 1 over 30, so that's equal to 30 centimeters. And then M2 is negative Q2 over P2. Negative 30 over P2, which is also 30, it's negative 1. Now our total magnification is the product of these two magnifications, so it's going to be plus 1. I could ask you either what is the final image position. In this case, it would be 30 centimeters to the right of the lens, or more likely I'll ask you what is the total magnification. All right, so be able to do that with your eyes closed, because it'll definitely be on there. I think that is the first question on the test. I'm pretty sure it is. Okay, so don't be surprised on Monday when you get it. Okay, here's stuff about the eye, Young's double slit, interference of waves. Can you read it okay? Here's some waves that are offset. Actually, these are offset by 45 degrees.
I was thinking like 90 or 45.
Right. Well, you're not going to see a 45-degree offset. Okay, so don't sweat that. Yeah, it's hard, but if they're not completely constructive or destructive, it's going to be 90 degrees. The 45 is hard to see. Here's one of those where you have to find the distance between the central and first bright fringes. That's where you have to do that tan theta thing. All right, you solve for theta, and then you find y. You good on that? Sure. It could be either for a double slit, a single slit, or a diffraction grating, but the process is the same. It's just, it will differ on how you find theta, because finding theta is different for single slit and double slit. But this is a double slit, so I first find theta. I say d sine theta equals m lambda. D is given, it's 0.04 millimeters. 0.04 times 10 to the minus, gosh, what is milli? Three. Milli is 3. Yeah, so times sine of theta. I need to figure out what is my order number. Well, it says first, so that means my order number is 1. And then my wavelength is 630 nanometers times 10 to the minus 9. Need to be pretty quick on doing those unit conversions. Just be able to write them down. Milli, 10 to the minus 3. Micro, 10 to the minus 6. Yeah, 10 to the minus 9. Okay, you'll need to know all 3 of those. Also, you might see centimeters, 10 to the minus 2. Though with the lens problems, all those measurements will be in centimeters. You don't need to convert those for the lenses, because the answers are going to be in centimeters too. See, if I find theta, I do the inverse sine of that 630 over 0.04. At 64 degrees. All right. No, that's not right. 0.9 degrees. Try it again. It's 0.9. Yeah, 0.9. Inverse sine, yeah. Okay, you get 0.9. And then once I get that, I say y equals L tan theta. So remember, I'm looking at my thing like this. It's a double slit. I found this angle right here. That's that 0.9 degrees. And now I want to find y. No L, so I say y is L tan theta. L is 1.6 meters. I know tan theta now, tan of 0.9 degrees. I get 0.025 meters. So B is the right answer. Okay, you're going to have one of these, so make sure that you can do it quickly. It sort of takes several steps, but you need to be able to do it fast, okay? That you don't even really need to think about it. Okay, find theta, now find y. 2 steps, find theta, find y. And doing all your unit conversions quickly as you go along, because you'll have a couple of unit conversions along the way. Okay. Yeah. Yeah, I understand. You're going to have one of these where you find the, what's the path length difference? Let's see, this one is 1, 2, 3 fringes over. So how many wavelengths is it, the path length difference? This is 0. That's 1. Oh, this is 2. So what is it? Right. 2 wavelengths. If it was a dark fringe, it would be some number of half wavelengths. Alright.
That's what I was confused.
Here's one of these, oh no, never mind. finding the number of the slit separation for diffraction grating, I just do 1 over 4,000, but that's going to give it in centimeters. 2.5 times 10 to the minus 4. So if I want to convert that now to meters, it's going to be 2.5 times 10 to the minus 6 meters. I have to move that decimal place over twice. 23, this is like when we saw the highest order maximum. If you see one of those, you just think right off, okay, theta has to be 90 degrees. This is my d value right here. This is my lambda. I say d sine of 90 equals m lambda, and I solve that for m. So m is d divided by lambda, because sine of 90 is 1. So that's, 1.7 times 10 to the minus 6 divided by 450 times 10 to the minus 9. I get 3.8. So that means I have 3 orders, not 4. And this is just asking for the highest order maximum, so the answer will be 3. If it asks for the number of bright spots, the answer would be 7. Right, because I'd have 3 on each side and the 1 in the middle. Yeah, so see, 3 is here. It also had 7, but the right answer is 3, because it's asking for the highest order, not for the number of bright spots. Okay? Y'all need it here? No. Okay. Alright, I'm going to have to go in just a few minutes. Any other questions that stand out to you?
Not much, surprisingly, like, this guy knows.
Okay. Is that all you have for now?
Yeah, basically.
Okay, I'm going to go ahead and pause this.
Some more.